Okay, so Unit 1, day number, whatever we're on here, 5, I think. Intermediate value theorem and squeeze theorem. And my face is frozen down here. I don't know what is going on here. Let's just try again. There we go. All right, intermediate value theorem and squeeze theorem. They're very much related to each other. They're very much obvious once you understand them, but until you understand them, it can sound technical and complicated. And then when you see what's going on, again, your reaction is probably going to be, we spent a whole day talking about that? That's like an important calculus discovery? Like somebody gets credit for figuring that out? Like that seemed pretty straightforward. Intermediate value theorem. So what's the word intermediate mean? Forget all the rest of this stuff. What's intermediate mean? Pardon? Middle. Some districts don't have middle schools. They have intermediate schools or junior highs. But intermediate means it's in the middle. And so this is going to be the in-the-middle value theorem. It's an example of an existence theorem, meaning the conclusion just guarantees that something exists. Again, it's not a conclusion that this great thing happened. It's just there's a value that exists. Okay, again, make it easy here. Susie weighed 7 pounds at birth, age 0 years. At 17 years old, Susie weighed 137 pounds. Must there be an age at which Susie weighed 86 pounds? What do you think? Not a trick question. Like, yes, there's no way that she skipped over 86 pounds. Right? Like, even if she was 85 one day, and then she ate a lot and was 87 the next day, like somewhere in between 85 and 87, while she's stuffing hamburgers in her face, like she crossed into 87, or she crossed through 86. Now, the technical term for what happens, or what that means, is the weight function is continuous. There are no jumps or holes or asymptotes, thankfully asymptotes, to your weight function, right? You might gain some weight, you might lose some weight, you might feel like your weight jumped, you might say that, but what you would mean is, gosh, over the summer I didn't do anything, I ate a lot and my weight jumped. Like, well, it might have jumped, but it didn't, if you graphed it, it didn't do that. That's not what your weight does. Again, even if you ate a really big meal, like it might go up like that, but it's still continuous. So there's got to be some age at which Susie weighed every weight between 7 and 137. She had to cross through all of those. This is the intermediate value theorem. The intermediate, or the in-between, or the middle, in this example was 86. She had to cross through 86. What other weights are guaranteed? What other weights did she have to cross through? There you go. So be a little more specific. All of them between 7 and 137. Is it possible she weighed 6 pounds at some point? You guys don't know this, but babies actually lose weight in their first couple days. So it's possible. Maybe she got sick, wasn't feeding right or whatever. Is it possible that sometime between 0 and 17 she weighed 140? Yeah, and then she stopped eating so much and worked out a little bit. But those aren't guaranteed. What's guaranteed, so we don't know what's happening outside of 7 to 137, but definitely everything between 7 and 137 occurred. And maybe more than once, right? Like, have a little bit of up and down there. Maybe it happened more than once. But it happened at least once. Everything between the extremes happened at least once. Okay, so here's all the fancy words that tries to say the same thing. If f is continuous, right, like if you really could like literally jump 10 pounds, like then this wouldn't work. But if it's continuous on a closed interval, meaning we want to include the endpoints, and the y values aren't equal to each other, although that would still be true. I'm not sure why that's on there. I guess because you want k to be a number between the extremes. Then there's at least one number c between a and b such that f of c equals k. Goodness, that's a lot of words. The y values are a and b. Or excuse me, the x values are a and b. The y values are f of a and f of b. So if you're going to get from the first point to the second point with a continuous function, then, I mean, maybe it goes up and comes back a little bit, but you're going to cross through everything in that intermediate band in there. Everything in there is going to have a y value. It's going to happen somewhere between a and b. If the y is between the y's, then there's an x between the x's. If there's a y between the y's, that's the intermediate part. Then there's an x between the x's, that's the other intermediate part. So if y is intermediate, then there had to be an x that's intermediate. If her weight is 86 in between 7 and 137, then sometime between age 0 and age 17, she had to weigh 137. And you said this earlier. Every y value between f of a and f of b must exist for some x value between a and b. Okay, let's see what problems look like, because it's like, okay, that seems obvious once you figure it out. How do we use that? Given that h is a continuous function, and then h represents the height of a tree at time t, so we don't have to justify that it's continuous. They just told us it's continuous. But that makes sense. Like trees growing, they may grow at different heights. But I feel like the height is continuous, unless you cut it down. H of t is meters, t is in years. Selected h values are given in the table below. Explain why there must be some time t at which the height of the tree is 17 meters. Okay, so this gets kind of formal here. So let me, you know what, before we do formal, you tell me. How do you know where, I'm frozen again down here, I don't know who knows when I froze either. How do you know, so forget the formality of the thing, just how do you know that the tree was 17 meters tall somewhere or sometime? Okay, because 17 is in the range. That's a good way to say it. Can you be more specific? When was the tree 17 meters tall? Between years 3 and 6. And that's about all you can say. It might have been 17 outside of those years. That seems doubtful for a tree, that it would grow and shrink. But the only thing you can say for sure is that 17 is between the y values, so there's got to be an x value, or a t value, I guess, what we're calling it, between 3 and 6. Now, let's see how we do that, like, formally or officially. You have to say that h is continuous, because this doesn't work if our tree could be like hopping around in height, then we wouldn't really know that it passed through 17. So you have to say it's continuous, and then you give a statement of the y values. So continuity, y values, and then your conclusion is going to be the x value. So let's see. H of 3 is 3.2. H of 6 is 19.3. And we have to write what you said, and maybe this seems silly, but you've got to say that what you recognize, that 17 is in between those two. 17 is between, and you could say between 3.2 and 19.3. You could say it's between H of 3 and H of 6. You could just write it as like an inequality. 3.2 is less than 17 is less than 19.3. Write it that way. But some way you've got to indicate that you know that 17 is the intermediate y value. And then your conclusion is an x value thing. So there must be at least one time, and between 3 and 6 is what you said, so I'm going to say 3 is less than t is less than 6, where the height is 17. So, the 3 steps for IVT. Say that it's continuous. And you might have to prove that it's continuous, or maybe they just give you that it's continuous. But say that it's continuous. And then think about the intermediate y value, because that's what you're looking for. And then your conclusion is the intermediate x value. I guess it's a little bit like continuity in that, like, conceptually super simple. Like, well, of course it goes through 17 meters at some point. But then technically, you've got to follow these 3 steps in order to use the IVT. Some people in their conclusion will say, according to IVT, blah, 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 but you don't have to cite the theorem. Just use the theorem. You can cite it if you want to, but you don't have to actually cite the theorem. Okay, that was a table. Let's do one with an equation. Given that g of x equals that thing, explain why there must be a value of c between 0 and 3 such that g of c is negative 1. Okay, if there must be a value on an interval, this sounds a lot like IVT is going on here. So between 0 and 3. So I'm thinking graphically, it helps me to like visualize this. So I'd like to know where the function is at 0 and 3. And this says that somewhere the function is equal to negative 1. So what do you think I should do to start this problem? You could also think about the 3 steps. Okay, so is it continuous? How do you know? And we didn't really talk about this. G of x is continuous because all polynomials are continuous. So you don't have to worry about polynomials. We like polynomials. Right? You haven't seen every polynomial. Nobody has, but you've seen enough of them. You've never seen a polynomial with a hole or a jump or an asymptote. So we're not worried about that. Okay, what are we thinking about next? said it's continuous. The y values. So how am I going to get the y values? Plug in 0 and 3. So let's find g of 0 and g of 3. And for this to work, negative 1 should be in between there, but I don't really know that yet until I find g of 0 and g of 3. G of 0 is an easy one. G of 3 takes a little bit of work. Let's see, 27 minus 9 plus 3 minus 2, so that'd be 18, 21, 19. Okay, so now I need to make like the intermediate value statement, and that is that negative 1 is in between there. So somehow you have to say that. So you can write it out, negative 1 is between negative 2 and 19, or you could just write it more simply, negative 2 is less than negative 1 is less than 19. Again, writing that statement feels a little bit weird. It's like, well, yeah, of course it is. But you have to include that because now you've recognized this is your y value statement. And then finally your x value statement is that, well, if the y value is in between the y's, then that means the x value is in between the x's. 3 little dot means therefore. So our conclusion is g of c equals negative 1 somewhere between 0 and 3. And again, you can write all that out in words, or you can be a little bit fancier and say 0 and 3 like that. Actually, I don't think I want brackets, because we know what 0 and 3 are. It doesn't happen at 0 or 3. It happens not at 0, not at 3, but somewhere in between there. Continuity, the y value is intermediate, therefore the x value is intermediate. Find the value in the interval such that g of c is negative 1. Find the value of c. Oh, okay, so like where does it happen? So what will we do to figure out the actual spot where the value is negative 1? There you go. Plug negative 1 in for the y value. Like set it equal to negative 1. So let's see. That doesn't look nice yet anyway. I'm going to add the 1 to the other side. Oh, that's okay. Because what can I do next? Algebra All-Stars. You remember the term for what we're about to do? The name of it? Yeah, factor by grouping. So let's take out an x squared. Take out a 1. So x squared plus 1 equals 0. Well, let's skip in too many steps. X squared plus 1 times x minus 1 equals 0. So either the first thing equals 0 or the second thing equals 0. That first thing's never going to be 0, but we can get x equals 1. And sure enough, that's between 0 and 3. We were guaranteed to get an answer between 0 and 3, and we did. All right. If the y is in the middle of the y's, the x is in the middle of the x's. That's the intermediate value theorem. Now, related to that is the squeeze theorem. or the sandwich theorem. If f is continuous, so here we go with our continuity again, and the graph of f lies between g and h for all the values in an open interval containing c, except possibly the c itself. It's getting complicated here. Let's start drawing a graph of this thing. So f lies between f lies between g and h. And then we have this comment that at c, the limit of g equals the limit of h. So that means that they have the same limit at c. We'll do different colors here. So I did g in red, I did h blue, and they have the same limit at c, and somehow I need to squeeze f, or sandwich f, in between g and h. So who knows what f is doing, but it's got to be in between g and h, which means at that c value, it's got to go right in between there, and then it can do whatever it wants after that. So if we squeeze it down, or sandwich it down, or pinch theorem is what some people call it, then it makes sense that our conclusion is that the limit of f has to be has to be L, because I got squeezed down, and if f is always between g and h, but g and h sandwiched it at that spot, then its limit also has to be L. Does that make sense? It's another one that's like, oh, there's a lot of technical words in there, but when you see what's happening, it's like, well, it couldn't really be anything else. G and h got squished together, and somehow f is right in between there. Well, it's got to be at the same spot that g and h are. It makes sense. Always dangerous when the calculus teacher says that, right? Our function always lies between two other functions, and those two other functions have the same limit. Then it's got to be that the limit of our function has the same limit. Yeah. Let's see how that looks in a problem. If f of x is not given, but it is known that f is continuous, and the graph of f lies between g and h, evaluate the limit as x approaches 1. Okay, well, I don't have an f to plug into, but I do know that it's in between g and h, so let's find the limit as x approaches 1 for g. And then we'll find the limit as x approaches 1 for h. And if those are the same thing, which I'm guessing they will be, then we'll have our answer. If they're not the same thing, then it would be answer D. If it doesn't squeeze it together, then we don't know what the limit is. So for G, 1 minus 2 is negative 1. H, we plug in 1, we get negative 1. So G goes to negative 1, H goes to negative 1. That means F has to go to negative 1. And in some sense, you ought to be thinking, well, I hope they're all like that, because, yeah, it either sandwiches to one value or it doesn't sandwich to a value. All right, number 2. If H is continuous, and it is known that the graph of H lies between the graphs of F and G, okay, so here we go again. I don't know what F and G look like, but H is sandwiched in between there. And we want to find the limit as x approaches 2. Well, let's see what happens when x is 2 for f and for g, and if those are the same thing, well then h will have to be that limit as well. So let's find the limit as x approaches 2 of f of x, and the limit as x approaches 2 of g of x. And again, if they're the same, then we got it. We got the squeeze theorem working. If they're not the same, then we won't have a conclusion here. So sine of 2 pi over 12 plus 5. Sine of pi over 6. What's the sine of pi over 6? Pre-cal experts. 1/2 plus 5. I'm just going to go with 5.5. And then for g of x, we're hoping we get 5.5, but let's see. 2 squared over 4 plus 2 over 4 plus 4. Let's see, that'd be 1 plus 1/2 plus 4. That would be 5.5. Okay, so what does that mean the limit as x approaches 2 of h of x is? It's got to be 5.5. If h is in between f and g are both 5.5, then that limit's got to be 5.5. Okay, but let's think about this. Justify your answer. We're using the squeeze theorem. So we have to say that, let's look back at the rules. Our function is continuous. H of x is continuous. And let's just go ahead and say, and between f and g, and then we've already got that these two are equal to each other. Therefore, the in-between limit has to be equal, because it got sandwiched in there or squeezed in there. So, two things today. Intermediate value theorem says if the y value is in between the y values, then the x value is in between the x values. Squeeze theorem is another sort of in-between theorem. If something is in between two things, and those two things have the same value, then the in-between function's got to go to the same value because it got squeezed in there.
Do you care if we write 5.5 as the limit halves?
That's fine. Yeah. Okay, so today's assignment is worksheet 5. It's on squeeze theorem and IVT. And some of it's pretty straightforward. But maybe more important is the review is in there as well. Calendar go with it. So I would say today's assignment is worksheet 5, but you might want to start looking at worksheet 6, because tomorrow I'll answer questions from worksheet 5. And then if you were in my pre-cal class last year, I'll do what I did where I record like half of the answers to one in one class and half the answers in the other class and post it all. So in here, tomorrow we'll probably work the odds on worksheet 6. And then in fourth period, we'll work the evens. And that way, by the end of the day, I'll have them all posted and you can check if you need to. So officially, today's assignment is worksheet 5 and tomorrow's worksheet 6, but we're going over both of them tomorrow, so I would at least look at some of them from worksheet 6, maybe thumb through there and see if you've got any questions or see if everything, looks manageable. Normally our reviews don't have 66 questions, but there's a bunch of them that are super quick. Like the first 18, you're just looking at the picture. So don't be intimidated by the 66 questions there. There's what our 10th graders were working on. Kingwood High does math during class Mondays. Micro, nano, pico.